Hello class, so today we're going to start 11.1, sequences, and it's our last chapter for the semester, so congratulations on getting this far. So the first thing I want to talk about is a sequence, and basically a sequence can be thought of as a list of numbers that are written in a definite order, so like A1, A sub 2, A sub 3, A sub 4, going to A sub n, and then going on forever, right? There's some notation that we should know about this also that's going to be important. And so if we have a sequence, if I give you a sequence, and the sequence looks very similar to what we just did, right, going on forever, this is going to be annotated or denoted as A sub n in brackets, or we could do A sub n in those brackets and then give it values for what it's going to. In this one, it's going from 1 to infinity. That's saying that it's going on forever. The other one on the left is basically implying the same thing, that it's a list that goes on forever. Okay, let's do an example, just so you guys can kind of get an idea of what's going on. And so we want to see if we can come up with a formula for the general term A sub n for this sequence. So the first thing that we want to do is kind of see if we can see something happening. So A1 is going to be 3/5. A sub 2 is going to be a negative 4/25. A sub 3 is 5 over 125, and we can kind of see it looks like it's changing signs and going up by 1 if you start at 3. So maybe one of the things that we can look at as we do this is, since we're starting at 3, let's see if we can figure out something first. The easiest thing to do is to see that the signs are changing back and forth, right? So we know that there's going to be a negative 1, and it's going to change every time. Now, since it's starting with an odd, or it's starting with a positive number, we need it to be either an even number or 0. And so we remember that n is going to always start like it's counting, so it's going to be 1, 2, 3, 4, 5. And so that means that this has to be n minus 1, because when I put in n for the first time, or the 1 for the first time, I'm going to get negative 1 to the 0, which will give me that positive for A sub 1. Remembering that this is n, these subscripts are the n, so that's important. Now, we also know that the numerator is starting at 3, so if we start with 1, if n is 1, how do I get 3? It looks like I need to add 2. So then at 2, I can see if n was 2, this would be 2 plus 2, that's the 4. If that's 2, that's 2 minus 1 is a negative, so that's a negative 4, so that's correct. Now we need to look at the denominator, and what we see in the denominator is we see looks like it's 5 to the first, then 5 to the second, then 5 to the third, 5 to the fourth, and it looks like it's just going a base of 5 to the n. This is the A sub n formula for the general term. These problems can get tricky, and so looking at the patterns and investigating them will take a little bit of time, right? But with looking at it and investigating it, you should be okay and be able to do it quite well. All right, let me go on to a sequence that you know very well probably. It's Fibonacci sequence, and we know Fibonacci sequence is recursive, and what recursive means is that it's built on by a previous term. So in Fibonacci, we know it's 1, 1, 2, 3, 5, 8, 13, 21, and then it's going to keep on, right, building on itself. So we know that the term f sub 1 is 1, f sub 2 is 1, but then it starts to do this pattern, right? And the pattern looks like this. It's f sub n is going to be f sub n minus 2, plus f sub n minus 1 when n is greater than or equal to 3. Now let me explain that to you. This n minus 2, so if this was the third term, right, which is the 2, if this was the third term, 3 minus 1 would give us the first term, so that would be a 1. And then this one would be 3 minus 1, which is the second term, which is 1. So then 1 plus 1 is 2. That would give us the 2. Now, if we went to the fourth term, it'd be 4 minus 2. And 4 minus 2 would be 1. Plus 4 minus 1 is 3, which would be this one. So 1 plus 3 is 3. And we see that this, in fact, does work for the Fibonacci sequence. But we start off with f sub 1 and f sub 2 is clearly defined being 1 and 1. Okay, now to get into some definitions. Instead of getting all crazy with the definitions about, I'm going to show you what it is to have a limit. And if it doesn't have a limit, then it's going to be divergent. So just an easy way to look at this is if I have a graph, right? And let's say this is the limit. And I'll do the limit in a different color. Okay. As I am plotting my points, each dot represents a sequence, okay? One term of a sequence, and we can see that as this function goes, as the sequence goes, it's tending towards my L. So as I go to infinity, my a sub n is tending towards that L. That's all the limit is saying there. If it doesn't go to a specific number, then we call that divergent, okay? All right. The next one is something that if you took Calc 1 and your teacher taught you 2.4, the precise definition of a limit, it talked about epsilon error. And so what this is saying is this: if we have that same graph, right? We have that same graph with our limit L here. And I plot some points, right? Trying to make it as close to what I had. There's potential for margin of error, so I'll use red for that. So L plus some acceptable margin of error is going to be here, and L minus some acceptable margin of error is going to be here, as long as my function falls within that margin of error, we are fine. That's all that's saying. But it is a definition that you should know, because we understand from the precise definition of a limit that there's always some potential error. Very, very small, but there is a potential error there. So now to go on to the next thing, it's a theorem. And all this theorem is saying is, in fact, what we've been pointing at is that if we have a limit that of a function as it goes to infinity is equal to the limit, then that function should be equal to the sequence a sub n. So, and then that sequence is going to have that same limit error. So, let me show you. If this is my L, I should do that in a different color, and it goes here. As I plot points, right, that are taking me to the error, the function and the plotted points are going to take me to that L limit. That's all that's saying. Okay? Okay. There's another definition. It's not that big a deal. Right here we have some limit laws that we're going to be used for sequences. These are very similar to the limit laws that we used in chapter 3. So for instance, if we have a sum of two sequences, they're taking the limit, you can take the limit of each sequence and that will be equal. Same thing with the difference. If you have a constant times some sequence, the limit of that, you can just take the limit of the sequence times your c. And then products, same thing. Quotients, same thing, but you have a restriction on the denominator. It cannot equal 0. And then powers follow that same thing. You can take the limit of the sequence raised to a power. That should be the same answer as taking the sequence powered and getting the limit. And then a constant, if you're taking the limit as n goes to infinity and you just have a constant, you're going to end up with just that constant, okay? These rules will be there for you and you'll be able to use them on the exam. But it's rules that you need to remember from chapter 3. If you can remember the rules from chapter 3, this is exactly the same thing that we had then. Okay. The next thing is the squeeze theorem. And the squeeze theorem, again, referencing something that we've done in the past. So we can see that we have a lower sequence and an upper sequence with some sequence in between. Well, if the lower and the upper have the same limit, the one in between must have that same limit. That's all it's saying. So basically, as one function pushes down and one function pushes up, the one in between, as the two extremes come together, the one in between must also come together. So here's one function, here's another function, right? Or a sequence, right? Let's just say there are a series of dots. Here is my B. We can see they're all going towards that limit L. Okay, it's basically squeezing them together. Some people call it the sandwich theorem. Yeah, it's just you're pushing the pieces of bread together, so what's in between the two pieces of bread is going to end up having the same value as our the two sequences above and below. Okay, we also have a theorem that says that the absolute value of a sequence, if it's equal to 0, then the limit of the sequence itself will equal 0. And so I'm going to demonstrate that for you soon, but I also wanted to demonstrate how we can attack some problems and do some examples. So in this first example, I want to see if a sequence is going to be convergent or divergent. Now remember, if it's convergent, it approaches a specific number. If it doesn't, if it goes to infinity or negative infinity, then we know it's divergent. So these are some skills and tricks that we learned from chapter 3 that are coming back into play. So what we're going to do with this problem is we know that we're going to go to infinity. So n is going to go to infinity of n over the root of 10 plus n. And we're going to do some tricks that we remember from the past. So I'm going to divide both top and bottom by n. So I'm going to get 10 over n squared plus n over n squared. And remember, if you have n squared if you have n in the denominator, but you put it into a root, you need to square it. So that's why I have the n squared there and there for you. And so my limit then is going to be the n as it goes to infinity of 1 over the root of 10 over n squared plus 1 over n. And what we end up seeing here is this is going to be equal to 1 over some tiny number, right? This is going to be tiny. And so 1 divided by some tiny number is going to take us to infinity. And since it takes off to infinity, does it converge or diverge? Remember, if it doesn't go to a specific number, it diverges. And so this case is going to be divergent. Okay? All right. The next example that we have is an oscillator. So we see that we have negative 1 to the n. So when it's anytime it's even, it's going to be positive. Anytime it's odd, it's going to be negative. And so this is a case where we're going to have to use that theorem of absolute value. So the limit as n goes to infinity of the absolute value of negative 1 to the n over n is going to be equal to the limit as n goes to infinity of 1 over n, correct? Because anytime that upper piece is oscillated to negative, it's going to become a positive 1. So I'm going to get this limit, and so 1 over some huge number is going to become 0. So because the absolute value goes to 0, we know that the function, by the theorem that we just talked about, of negative 1 to the n over 1 is going to be equal to 0. Okay? And there's my answer to that one. So very, very cool. Okay. Again, using some of the rules that we have, here's another theorem. If the limit as n goes to infinity of a sequence is equal to some L, and the function is continuous at L, then the f of the sequence is equal to f of L, meaning some function that has all these sequential points is going to be equal to the limit of the function evaluated at the new limit. So fancy speak for this, limit rules, right? So we know that if we have this internal theta over n for sine, we can rewrite that so that it's taken care of this way. So that now sine, because sine didn't have anything to do with the n, we can move it in. So all it's saying is, you see that this limit here is going to be L. Sine is the function, correct? So then when I get the limit of the inside piece, which ends up being the limit, whatever that limit is, sine of L is this piece. So fancy speak for that, right? Now we know that as n goes to infinity, pi divided by infinity is going to go to 0. So I'm going to get sine of 0, and sine of 0 is 0. So there's our answer for this one. I hope that makes it very clear for you. The limit of the function, or the limit of the sequence, is L. So the limit, this is my sequence. When I take the limit of it, that is going to be evaluated with the function, which is this piece here. Okay? This one here takes us back to probably geometry and trig, right? So this is the geometric, the geometric series or sequence. And so since it's geometric, we also know that the geometric sequence had convergence if it was within negative 1 and 1. And then if it was outside of that, it would diverge, right? It would take off. So that's important to know. Just remember that. That's critical. So it converges if we're within, or what I mean by convergent when you had it in geometry before is you got some value number, right? Anything bigger than 1, the absolute value of 1, would make, or absolute value of r, would make it not a sum you could do. So that's what this is saying. And then some terminology that's going to be important is here, monotonic. And all monotonic really means, a simple way to think about it is if you take the derivative of a function, if it's always positive, it's monotonic. If you take the derivative of it and you get a negative and it's always negative, that's monotonic. Meaning it's either all increasing or it's all decreasing. That's all you need to know about the fancy word monotonic. Okay? It's either increasing or it's decreasing. Okay? So what we want to do is demonstrate that. So show that the sequence a sub n is equal to n over the quantity n squared plus 1. And so to do that, what we're going to do is we need to show, and it's something that's I should write down for you. We must show that a sub n plus 1 is going to be smaller than the previous term, right? So if I go to the next number should be smaller, not bigger, if I'm trying to show that it is decreasing, correct? So that's important. We need to show that it's going to be smaller. Okay, so one of the ways to do that is, how do I show the next term if I don't know the number? Everywhere I see n, I'm going to have to make it n plus 1, right? Because that's what the notation's saying, right? I'm going to put n plus 1. So n plus 1 over n plus 1 squared plus 1 should be smaller than n over n squared plus 1. Okay, so I'm going to cross multiply here. So I'm going to get n plus 1 times n squared plus 1. That should be less than n times, bracket that, n plus 1 squared plus 1. And this is going to become n cubed plus n squared plus n plus 1. And over here, I'm going to get n cubed plus 2n squared plus 2n. All right, and so we see some things are going to cancel. So I'm going to get we're going to get 1 is less than n squared plus n, right? Here, you know what? I can show that so you guys can see. So the n cubes will go. We're going to be left with an n squared on this one, on this side, correct? And we're going to be left with an n. The only thing left on that side is going to be that 1. And so what we see is 1 is less than n squared plus 1. Now, we know that our sequence is always going to start at 1, right? So since we start at n equals 1, really what we should say, well, that's fine. Start at n equals 1. The smallest term that we're going to have is 1, right? But if I put 1 in there, 1 squared is 1 plus 1. That's going to give me 2. Is 1 less than 2? We know that's true. So that tells us that we know, and that's the smallest one, so anything bigger than that, it's going to also be true. That means that we know that n squared plus n is greater than 1 is absolutely true. And since that's true, that will imply that n plus 1 is less than a sub n. So the sequence that we're given is going to be decreasing. Okay, now the important thing here is just to remember that. And remember, just pointing that out again so you guys can see, this is the side that represents a sub n. This is the side that represented a sub n plus 1, right? Because when we did it, this was a sub n plus 1. This was a sub n, following the math, which in fact shows what we're trying to demonstrate. Okay? All right. Here's a definition for bounds, and all this is really saying is this sequence. Let me draw it in a picture so it's probably clearer and easier for you to all understand. So if this is my limit, correct, here, and I have some value that's even larger up here, some m value, okay, and we know that that's where it's bounded. If we plug in a bunch of sequence points and it ends at the limit and it never crosses my M, my capital M, right? Then we know that this is bounded above. By the same reason, if we have something that's bounded below, it never crosses that lowercase m as a lower bound. Okay? That's all this is saying, is that something approaches some potential limit or some bound, but it never crosses that hard bound. So basically this is saying that our function, in this case, in this picture that I'm showing you, is definitely bounded above. Okay? If I had inverted it, and I had the lowercase m, that would be something that is bounded below. Okay? Now, if it's bounded by both, right? So let's say that this function only went to that 0 and I made this my lowercase m at the x-axis. This would be bounded above and below, right? And so if it's bounded above and below, it's called a bounded sequence. Okay? And that's only when it's bounded above and below. All right. Let me show you one last thing. As you can see, a lot of this that we have definitely is functions and going back to chapter 3 of Calc 1. And so refreshing your mind to attack these problems with knowing your limit laws will be beneficial. And then understanding sequences, right? But this shouldn't be too difficult for you all. It should be something that is manageable. All right, let me show you this last thing, this last example I want to show. Now remember, when I talked about monotonic, it's either strictly increasing or strictly decreasing. And so what this is saying is that every bounded monotonic sequence is convergent. So all it's saying that if it's monotonic, it's bounded, it's going to have to come to a specific number. And so I can demonstrate that for you. But just remember, it's going to go to a specific number. Now, one of the things that I want to do is show you a method to investigate this. And so the way we're going to do it is we're going to have this sequence, and they're telling us the number that we start with, and then they're telling us the actual sequence. And it's 4n going from 1 to infinity, right? So just so that we understand what's going on, I want to take you through every step on this problem and be able to demonstrate that this is actually making sense. So if a sub 1, I want to go back to black, if that's okay. If a sub 1 is 2, a sub 2 should be, if we follow the rule, it should be 1/2 a sub 1 plus 6. So that's going to give me 1/2 2 plus 6, which is going to give me 8. Half of 8 is 4. So then a sub 3 is going to be 1/2 a sub 2 plus 6. So that's going to be 1/2 4 plus 6, which should give me 5. Right? A sub 4 then will be 1/2 5 plus 6, which should give me 5.5. A sub 5 would be 1/2 5.5 plus 6, which will give me 5.75. And then I'll just do one more just so we can kind of see, or that's probably enough. So what do we see is happening to our values? It's going from 2 to 4 to 5 to 5.5 to 5.75. We can see that the function here looks to be increasing correctly, right? So it looks to be increasing, right? So we can see that this is something that looks to be monotonic. Okay? Now, one of the methods to attack these problems and to look at them to see that this is a function that it's increasing is to use the induction steps. And we can do that quite easily. So, and we can even see where this thing is going, right? So I'll demonstrate that for you, what this function ends up going to. But we can see that this thing is definitely showing us something that is, it's growing, right? Ever so slowly. So the way that we do this is we're going to go, okay, A of k sub 1 should be bigger than A sub k, right? So the previous one. This is it's called induction investigation. I'm going to the next term to see what's happening. So I'm going to say, okay, so if that's what we have as our term, then by definition, if I add 6 to both sides, the function should still hold true, correct? And so from there, to make it look like the function that we had, right, multiplying both sides by a half still holds true what we were saying. Isn't this by definition the next series term? So shouldn't that be AK plus 2? And that should be bigger than this one, which now isn't that the next term, which would be A of k plus 1. So what this is going to tell us then is that A of n plus 1 should be bigger than A sub n. This is true for n when it's k plus 1, right? So what this is showing us there is that the inequality is true for all n by this thing called induction. So what I demonstrated there is when I substitute in instead of n plus 1, we can show that the function is steadily increasing. Now, one of the things that we also want to be able to show and verify is that this thing is bounded, right? And so let's see if we can see that it's bounded. So we can see it looks like this thing is going to be less than 6, right? For each term, it looks like each term is less than 6, right? Because we got to 5.7, the next term would have been 5.87, and every individual term would have tended to be something that was less than that 6. So what I want to show you is this. So we can say that if A sub k is less than 6, then A sub k plus 6 should be less than 6 plus 6, which would be A sub k plus 6 is less than 12, correct? And then if we half 1/2 A sub k plus 6, we're going to get 1/2 12, right? And that's going to be 1/2 of A sub k plus 6, which is going to be less than 6. And remember that this left side is the next term. So that would be A sub k plus 1. That's going to be less than 6. So what this is showing us by, again, induction, is that our A sub n is going to always be less than 6 this is for all of our n's. Okay, I should probably write that down so you guys know. That means for all. So what's cool about that is what it ends up demonstrating for us is that this thing is bounded, and it's bounded so that it ends up equaling 6. So I can show that to you. So here's how I do it. I'll go the limit as n goes to infinity of a sub n plus 1, which is equal to the limit as n goes to infinity of 1/2 a sub n plus 6, right? That's the definition of a sub n plus 1, which will equal 1/2, because that has nothing to do with the limit as n goes to infinity of a sub n plus 6. And we know that this piece here is going to be a limit. So I'm going to get 1/2, I'll call it L, plus 6. And don't we know that since a sub n is going to go towards L, I should say going towards L, it follows then that a sub n plus 1 should also go to L, right? Because, just so you understand the reasoning, as n goes to infinity, isn't that the same as n plus 1 will go to the same infinity or to a similar infinity? So what we end up seeing is L is equal to 1/2 L plus 6. We multiply to get rid of the half, and we see that this thing ends up bounded to be equal to 6. So this equation, I know there's a lot to it, you'll probably want to look at it again. Not only is it a sequence that is monotonic, which I showed, right? It was increasing by this up here. This showed that it was increasing. Then I was able to demonstrate by induction that it was going to be smaller than 6, right? The value of it was going to be smaller than 6 for all n. It would get closer and closer to 6, but never go beyond 6. And then I showed the proof for the limit equaling 6. This might take a little bit of time and comprehension, but my advice is watch this again and again, and I'll be able to answer questions for you on this either Wednesday or next Monday. Okay? I'll put up the homework for 11.1, and I'll also be posting a video for 11.2, so you guys can have that homework also. All right? Practice these problems. They should be very doable. And email me if you have any questions. All the best.